Begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for the weekend that's about to start. Help us to glorify you what we do here this day. And I just, again, Lord, thank you for these students. I pray that you would encourage them as they work on this class to persevere and just to do their best, Lord, every day, Lord. In your name I pray. Amen. All right. Let me assess the damages. We got... All right. Let's see what we got here. How many today know what the definition of the convergence of a series is? There's one. Oh, man. Two. Three. Wow. 4. Holy cow. If you believe in that sort of thing. Let's see here. I would say that we should write, this is equal to the limit as n goes to infinity. I would just, one I'm just looking at right now, doesn't have equality there, has an arrow. And I would say that's not optimal. And, oh, good grief. Yeah, that's, you guys influence me. See what you've done to me? It's from looking at yesterday's. It's actually, who knows what I'm going to write so many wrong things today, you just don't even know. There we go. Yes, that's the definition we're looking for. So one of you has an arrow instead of an equals there. I would discourage that. Yay! Another? Hey, I think we have gone from 4 of you knowing to maybe 4 of you not knowing. Let's see here. That one's right. This is very encouraging, guys. All right, I think I've done enough. All right, so good. Much improved, much improved. Now, how about this next one? How should we do this? Oh, goodness gracious, yes, thank you. Or I should put an n here, one or the other. So, okay, so notice that 1 over k cubed plus 2 is what? This is less than 1 over k cubed. And the sum, 1 over k cubed, k equals to, I guess I should do 1. 1 to infinity. Okay, fine. I'm sorry, I didn't mean to make this complicated. I'll talk about this issue here in a second, but I wanted to put a 1 there. I'm sorry, guys. So that's what I meant. I mean, I didn't want to make that 0 an issue here. We'll talk about that soon enough here. This is converges by what? It's the p equals 3 series, right? So by direct comparison, by the direct comparison test, we have that I was trying to be lazier. Let me call this thing S. S converges. It's a convergent series, all right. Now, how about this one? Here we have a sub k. Oh, man. And look what I've done. Look what I've done. That one doesn't even make sense at 0. Oh, I tell you. This is just it's a bad making problems up day. I should put a 1 here, obviously, or something so that at least it's well defined. Like I was saying, that means that I didn't spend enough time making the problem. But you saw me make the problems. It took me 3 seconds. You watched me do it, and that's what happens when I do that. Anyway, so here we go. I promise you I will take more time to make your test. Let's see here, 3k plus k squared. And what do you notice about that kth term? I hope you understood the spirit of my problem, if you weren't distracted by my stupidity at the 0th term. Yeah, this goes to 1, and what does that mean? It converges, right? It converges to 1. Right, the term converges to 1, the sequence a sub k converges to 1, but that does not give you convergence of the series. That is not 0, right? So therefore, I was going to give this a name. let me call it S tilde there. Therefore, S tilde diverges by the kth term test, which we proved last time, right? So if the kth term does not go to 0, game over, it diverges. Yep.
There are other methods to, like for Q2, there's other methods of finding the convergence, right? Besides doing the comparison.
None that we know yet. How did you do it?
I just calculated the n partial sum.
You calculated the nth partial sum for that? That would be epic. Like, that would be amazing. The nth partial sum for that is quite, I mean, you just looked at numerical evidence, you're saying? Yeah. But numerical evidence can be deceiving, right? If we look at the harmonic series, 1 plus a half plus a third plus a fourth plus a fifth, so forth and so on, it's not getting big very fast. So you might think that it converges. And it's true that it diverges very, very slowly. I think it takes like 1,000,000 terms for the harmonic series just to get to 20. You have to add up fractions up to like 1,000,000 to get to the sum of fractions to be 20. But it still blows up, right? So like numerical evidence is very dangerous, unless you've got some sort of systematic reason that it's canceling. Let me show you one that there's such a cancellation. Since you brought it up, it's a little bit out of order here. But something that has that kind of cancellation that you can see will be this one. This is the so-called alternating harmonic series. So the way this is 1 minus 1/2 plus 1/3 minus 1/4 plus da 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 da. Right? And you can actually picture this one. You can picture the nth partial sum. It's like here's 0, here's 1, right? So what is S1? Right here is S1, right? The first partial sum is there. Where's the second partial sum? See, these first two terms are S2, right? So that gives me a half. All right. And then the first three terms are S3, right? That gets me over to here. Yeah, so I have to add a 6 to that. So it's you say 5/6? Yeah. And S4, the first four terms, right? So I subtract a fourth, that puts me like in here. All right? And then you see what you're doing? You're doing this one step forward, a half a step back thing, you know? I don't know how to work natural log of 2 into a song, but eventually you converge to natural log of 2. So there's a huge difference between just adding these with all pluses versus adding these with plus minus, plus minus, plus minus. There's a systematic cancellation that happens that ends up making this actually converge to the natural log of 2. Now, we don't have the tools yet to prove that, but it's true. Oh, okay. But no, I don't know another method to show that this converges. I guess you can integrate dx over x cubed plus 2. I don't want to do that integral. That's not a pleasant integral. So integral test is kind of out, right? Okay, so we want more tests. We want more tools, right? I would like to make some observations here before we get to that, though. Suppose this is reverse. I'm going to do a reverse engineering. So suppose S sub n is equal to the sum, k equals 0 to n of a sub k, all right? Imagine that you're given this, all right? So for example, it could be inverse tangent of n. Suppose that that works out to inverse tangent of n. What terms give you this partial sum? I'm asking a really weird question for the moment. This is a little bit outside our larger story that we're telling here, but it's a fun thing to stop and do. How would you get, really the question I'm asking is, how would you calculate a sub k from the nth partial sums? We kind of ran across this in the proof of something yesterday, right? How about this? If we take Sn minus Sn minus 1, what's that? That's the sum k equals 0 to n of a sub k minus the sum k equals 0 to n minus 1 of a sub k, right? Which, by the way, is what? A sub n, right? So with this little observation, this implies for my made-up example that a sub k is equal to what? Looks like it's inverse tangent of k minus the inverse tangent of k minus 1. In this sense, in some sense, every series which converges is actually a telescoping series. You could rewrite it as a telescoping series in this sense, right? Like if I just forget about the man behind the curtain here and look at this example, the sum k equals 0 to infinity, inverse tangent of k minus inverse tangent of k minus 1, right? This is pretty transparently a telescoping series. Calculate its nth partial sum. What is its nth partial sum? So we do inverse tangent of 1 minus inverse tangent of, well, I guess minus 1 in this case, right? Oh, 0. I'm an idiot. Sorry. Thank you. And then plus the next one, right? Inverse tangent of 2 minus inverse tangent of 1. And yeah, this is k equals 1. Here's k equals 1. Oh, yeah, I'm sorry. That's what's confusing me. Thank you. I wanted to put a 1 there. Thank you very much. K equals 1. Why didn't I put 1s over here? It doesn't matter. You can put it at 0 or at 1. It's more natural here if I put it at 1, though, right? There. Is that better? Now they're all matching. Sorry. So you keep going until you get to n, right? Well, I'll do n minus 1. K equals n minus 1 gives me inverse tangent of n minus 1 minus inverse tangent of n minus 2. And then finally the last one, inverse tangent of n minus inverse tangent of n minus 1. This is about enough to make me start using arctangent, inverse tangent of n minus 1. And you see what cancels, right? Well, oh yeah, this one and that one, right? This one with something I haven't written over here, right? And it's like that one and that one cancel. This one cancels with something I wrote over here, that I haven't written. So all that survives is this one and that one in the telescoping, and you get Sn is equal to inverse tangent of n minus inverse tangent of 0, right? Which of course is what? So, oh, Yeah, sorry, confusing myself. And then you take the limit as n goes to, what have I done? Yeah, and then you take the limit as n goes to infinity, what do you get? What's the limit of inverse tangent as n goes to infinity? Yeah. So in other words, this is pi over 2. Anyway, I mean, this is it's a cute comment to make that if the nth partial sum converges, you can look at it as a telescoping series, right? But pragmatically speaking, since we can't usually calculate the nth, I mean, I don't know, it's a lot of the time you can't find this formula, so to speak, for an actual series. So it's hard to really see every series pragmatically. Like, this series converges. It's not that easy to see how it is actually a telescoping series. All right. Anyway, I shut up. I've said far too much about this already. Okay, so something I promised to talk to you guys about. This example comes to you from the future. This is from the alternating. This is an example of an alternating series. We get to that in a lecture or two. So, first few terms. Let's talk about the first few terms. So if I have something like the sum, you know, k equals 3 to infinity of 1 over k squared, let's say. I would say intuitively that is the same thing as the p equals 3 series. I know literally it's not, but how are the p equals 3 series and this related? P equals 2, I'm sorry, p equals, good grief, what's wrong with me? Yeah, I told you I was going to say stupid things today. I made good on that. Let's see here, so p equals 2. How is this related to p equals 2? P equals 2 is what? That one starts at 1, right? The official one anyway. So I'm trying to show you that off-brand p equals 2s are still the same thing, really. This is kind of an off-brand one, you know, it's missing a few things. You've subtracted what from it? The first term, the second term, and I guess that's it, right? So there's a little theorem. This is finite, right? This converges. If you have something that's finite plus something that converges, it follows that that also converges. So if you can see a series as being just something you already know converges, missing a few terms, right? Or perhaps adding a few more terms, right? So a different version of this would be something like, suppose I have some k equals minus 2 to infinity. Oh, k not equal to 0. There, phew. 1 over k squared. So what would that be? That would be, you know, 1/4 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 9 plus dot 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 dot, right? So I'm throwing out 0. So this is the p equals 2 series, and this is a little extra. This also converges. You can add a little bit. You can take a little bit away. It's the same convergence, right? Here's another example of this way of thinking. What if I have the sum, k equals 0 to infinity of 1 over, let's say, k squared plus 4k plus 5. Oh, maybe, no, I want 4k plus 4. All right, so this is really equal to the sum. Now, I know you could do direct comparison, but I'm trying to show you a different way to think about it, okay? This is 1 over k plus 2 quantity squared, right? So another way I could look at this problem is to make a substitution, right? I could rewrite this as the sum. I could let j equal k plus 2, right? And then what does my j start at? If k starts at 0, where's j start? -2? Yeah, if I put 0 for k, I get j is 2, right? So j equals to 2. And if k is infinity, j is infinity, so that's fine. Same song and dance. 1 over j squared. But again, this is the p series. This is p equals 2 series missing a term, right? So this converges. I would say this converges. It's an off-brand p equals 2 series. There, that's some technical terminology. You guys can use that if you like. That's just for this semester. People will make fun of you if you use this terminology outside of this class. They won't know what you're talking about. All right, I just made it up. It seems reasonable. Any questions? What's that?
What's it actually called?
I don't know if it has a name. I mean, it's like a p equals 2 series, but it's not quite a p equals 2 series because it's missing the first term, you know? You might say it's a shifted p equals 2 series. All right, these are different tricks we can do to analyze these problems. But there is sort of a, you know, I show you these, but you're not, you will, after I show you the next theorem, you're never going to use these because this theorem just does these problems easier. Fine, you got me, I admit it. Yeah.
So does it kind of work like a substitution where it's like you just substitute what you need?
Yeah, it's exactly just like a U substitution. I think it's very much what it's like. Sorry, I'm trying to find the statement of this thing so I don't make, I mean, it's very important to check on the preconditions for these theorems as we apply them, all right? Because if you try to apply these theorems where they don't apply, they will lead you astray, you know? The preconditions, the hypothesis for the theorem are important. So here's the hypotheses. We are going to let the sum, and this notation is pretty nice. What does this notation mean? What does it mean when you write the series without the lower bound? I mean, the starting point. What's the idea there? It could start at 0. It could start at 1. It could start at 3. It could start at -7. It doesn't matter. It's got a starting point, and they share a common starting point. Actually, it doesn't even matter. If they don't share a common starting point, you can add 0 to one of them to make them have the same starting point, right? You ever think about this? If I wanted to add, if I had, you know, a0 plus a1 plus a2 plus and I wanted to add it to b2 plus b3 plus how would I add these series? I just define the 0th terms here like that, you know? So I just put some extra zeros in the b series and then I can add them. I can treat them both like they're series that start at 0, even though the b series originally started at 2. Right? You can adjust them so they have the same starting point. One of them's got to have a smallest starting point, so just add zeros to make the other one fit. All right, so my point is, it doesn't matter where they start, but they are series with positive terms. And then here's the deal. If a sub k over b sub k goes to L, and L is positive, then they are inextricably linked. The series with a sub k converges if and only if the series with term b sub k converges. In other words, if one diverges, the other one also diverges as well. Right? Before I prove this theorem for you, let me just take a second to apply it to this problem. So, for example, I can look at, a sub k equal to 1 over k squared plus 4k plus 4 versus b sub k equal to what? What would I compare this series to? The what? 1 over k squared, right? It's essentially a p equals 2 series, so compare it to a p equals 2 series. What happens when you calculate a sub k? These are both positive terms, right? If we have k greater than or equal to 1, those are positive. So they fit the conditions for the limit comparison test. By the way, this is called limit comparison test, or LCT. Yeah. The one I did last time is the direct comparison test. Some books call it, your book might call it the basic comparison test, I forget. But I like to call it direct comparison test because it's the direct comparison test. That just makes sense, the terminology. Okay, so a sub k over b sub k, what do we got? We've got k squared over k squared plus 4k plus 4, which goes to 1, right? As k goes to infinity. Of course, 1 is greater than 0, therefore the series, I'm trying not to rewrite things. Let me give this thing a name. I'm going to call it Pac-Man. Therefore, Pac-Man converges since the sum k equals 1 to infinity of 1 over k squared converges by p equals 2. Series test. Or series result, or just p equals 2 series if you like. As you can see, this requires far less cleverness than this, right? Like this is a little bit sneaky. This substitution business up here, a little bit sneaky. This adding or subtracting terms to see it's the same as a series, a little bit tricky, right? Limit comparison, just no-brainer. I mean, it's just, you just look at the quotient of the things and it just beats it to death for you. Oh, I'm sorry, it's too violent. Let's see here. So I forgot, some of you may have been raised by series. I should be careful. Another example, before I get to the proof. If I have the sum k equals 1 to infinity of 1 over, I don't know how this is going to go. This might not work. I'm going to try it though. K plus log k. See, I don't know. I mean, that's kind of, well, is it positive? Log of 1 is 0, right? So this thing starts at 1. Log of 2 is 0.693. It's fine. It's positive. So we can at least apply limit comparison. What do you guys want to compare it to? Yeah, p equals 1 series. I like that, to the 1 over k, right? Let's compare it to the harmonic, see what we get. So we're going to let this be a sub k. And so we'll look at a sub k divided by 1 over k. So we're going to compare to the p equals 1 series. And so we got what? We got k divided by k plus log k. Do you guys know what I'm doing here? I never write fraction over fraction. What do I do? The denominator of the denominator is the numerator, right? So I just flip it. See what I did there? I just put this k up here, right? And the a sub k is 1 over k plus log k, so I just put it down there. How about this limit? I think we should extend k continuously and perhaps try the L'Hopital's rule here, right? Because what? It's infinity over infinity, right? As k goes to infinity. So extending k continuously,
What do we need to write it?
L'Hopital's rule, infinity over infinity. This is 1 over 1 plus 1 over k, which of course goes to 1 over 1 plus 0, woohoo, which is 1, which is greater than 0.
You don't have to write it as a limit.
This is limit right here, limit
Oh.
extended k continuously. So sometimes the limit notation gets in our way, and so we can use the arrow notation, if you like. But I should probably say something somewhere in here. You know, usually you say it off to here, you know. We let k go to infinity. I mean, it's fairly unambiguous, right? There's only one kind of limit you take with a sequence, right? You're not going to take the limit as k goes to 7. I mean, it's a discrete variable. The only interesting limit to take is the one at infinity, as far as I know. Okay, so limit comparison test. Thus, by limit comparison test, the divergence of p equals 1 series is inherited. Well, I don't know what you want to say. It's shared. It's gives. Oh, I don't want to write that again. I'm going to give it a name. It gives the ghost divergence. Divergence, yeah. This is a generic ghost. I mean, you can give it a name if you want. Sam, Ringo,
I just can't remember my pack.
off-brand ghost. You have a question?
I just wanted to ask you played Pac-Man
Do I play? No, it's mostly because if you try to draw SpongeBob or something more interesting, it's really hard. But Pac-Man and Ghost are really easy to draw on the fly. I also can do stickmen. Stickmen, like little stick figures. And a certain, some fishes, yeah. Because this is a divergent series. P equals 1 series is our quintessential, just barely diverging series. P equals 1 harmonic series diverges. So by limit comparison, the quotient of a sub k over b sub k is 1, which is positive. Limit comparison applies. And so the fact that 1 over k did not converge forces this to also not converge. Yep. It either converges or it doesn't. So these are mutually exclusive categories. There's no like half converges, half diverges, right? If it doesn't converge, it diverges. Yeah.
So if it was less than 0, it wouldn't tell you anything.
Yeah, if the limit if it was less than 0, it would be truly mysterious because these are the quotient of positive terms. And so if that came out to something less, that would mean that I did a calculation wrong. What you want to ask me is, what if it went to infinity? If it went to infinity, I don't know. Or the other thing that could happen is it could go to 0. So 0 or infinity, I don't know. But for positive term, it'll work. It should work. If it works out to a finite positive thing, then limit comparison applies. It's just a quirk of our examples that worked out to 1 both times. Like if I put if I do something like put a 2 here, you know what'll happen? That puts a 2 here, which makes this a 2, you know? So it doesn't have to work out to 1. It can work out something other than 1. Just a matter of relative sizes of things. How much time do I have left? I forgot my watch. Am I 5 minutes? Okay. We're good. So the question then is the proof of the limit comparison test. How do you prove the limit comparison test? So going back to, you were asking me, like, you were saying if I did the k squared, k cubed over 2 example a different way, what I was kind of expecting you might have told me was I used the limit comparison test. Because sometimes people have had calculus before they've had it with me, and they might remember that. And if you've had calculus 2 before, and this is one of the parts of the course you understood, you would remember limit comparison test is super useful. And it gets us out of a lot of corners. But anyway, here's the proof. So we're going to suppose that we've got some a sub k and some series formed by b sub k with a sub k, b sub k greater than 0, positive terms, right? And we're going to assume that the ratio a sub k over b sub k goes to L as k goes to infinity. Sorry, my k's are kind of degenerate. My k's are just ugly. I admit it. They're so hideous. So what this means is that for k sufficiently large, for k greater than or equal to some n, what can we do? Well, I'm sorry, I've forgotten something here. Let's see here. Let epsilon be between 0 and L. Let's see here, what am I trying to do? I'm trying to prove that this converges only if that converges. Let's see how this happens. It's actually going to be by the direct comparison test here, so just give a second here, we'll get to it. So I should actually, I'm sorry, I'm supposed to put that before that. It doesn't really logically much matter here. But anyway, so we're picking some epsilon between 0 and L. Because this limit exists, there exists some n in the natural numbers such that what? Such that if k is greater than or equal to n, then the absolute value of a sub k over b sub k minus L is less than what? Less than epsilon. This is what it means for that limit to exist, right? It means that the terms in the quotient terms, right? If you go sufficiently far out, they're within epsilon units of the limiting value. And you can do that for any epsilon you like, as small as you want. All right? But we just pick some epsilon between 0 and L. Okay, so then what is this? So this is just definition of the limit, which you guys were still you're still upset that I didn't test on that, I know, but you'll get over it? No? Okay, sorry. So minus epsilon less than a sub k over b sub k minus L less than epsilon, right? That's how we unwrap an inequality with absolute values. And then what? Add L? Yeah, it seems like a good idea. So L minus epsilon less than a sub k over b sub k less than L plus epsilon. Then what? Multiplied by bk? Now, yeah, why can I do that? So Nathan's telling me I can do that because we assume b sub k was positive, right? So you can't multiply. If you multiply an inequality by a negative thing, you flip the order of the inequality. If you multiply by a 0, you destroy the inequality, right? You lose information. There's that, right? And that's it. That pretty much proves it. See, because now we just have to think about cases and the direct comparison test, right? So think about this. If the a sub k, if the sum of a sub k converges, right? That means that this, which is, by the way, how do I know that this is positive? I know that 0 is less than or equal to that, right? Actually, not even equals, but less than that, because I'm assuming that epsilon is between 0 and L, right? So that one of the things that means is that 0 is less than L minus epsilon. Okay, so that makes this positive. So I'm comparing a positive term to a positive term. If the a sub k converges, that forces L minus epsilon b sub k, right, to converge. But remember what this is equal to. That, right? You can pull the constant out. And so if we have convergence of a constant times a series, it follows that the series is also convergent, right? So convergence of the series formed by a sub k forces convergence of the series formed by b sub k. Conversely, if the series formed by a sub k with term a sub k diverges, then here you have something smaller diverging that forces this also to diverge. But if this diverges, it's a constant times the b sub k series, so it forces the b sub k series to also diverge. So basically, limit comparison is a simple consequence of direct comparison and the definition of the limit, right? But to actually go through these details for a specific example like the two we just did would be awful, right? To actually implement this idea at the level of this proof would be awful, but the thing is we don't have to, because we can use limits, and limits have many privileges that we are entitled, right? You know, we have rights that we're entitled to, and things we can use like L'Hopital's rule, you know. And so the limiting concept is so very important. If we always had to do limits with epsilons and deltas, epsilons and n's, we wouldn't get very far, would we? You know? But thankfully, we do those things for some proofs and to understand them, and then to actually work problems, we use algebra mostly, right? Anyway, I think I'm out of time, so we will. So just to give you a sense of what you should be working on, let me tell you guys. We are basically up through, give or take a thing, basically sections 12.1, 12.2, 12.3. So you should be working on the homework from 12.1, 12.2, 12.3, all right?
We have a quiz on Monday, right?
Yeah, we'll have a short quiz on Monday. It won't be as long as usual. It will not be bonus, though. It'll be for points.